In this analysis, we're going to take a look at the drawing of bimetallic wire. So you may be familiar with wire drawing. If you have a large diameter wire and you want to make a smaller diameter wire, you pull it through a die. It's a reducing die, and it makes the wire smaller through plastic deformation. Now with a bimetallic wire, this would be a situation where we have maybe a steel core and a copper jacket. That's a pretty common configuration for bimetallic wire. It's very useful if you want to save some cost, because the steel is usually cheaper. It gives you higher structural properties because it has the steel core, where the copper tends to be a little bit softer. And it also preserves a lot of the electrical conductivity. So there's a company called Copperweld. It's now Fushi Copperweld that back in the 20s they developed this process of drawing bimetallic wire, and it's kind of evolved throughout the years. Again, the basic idea is we start with a larger diameter and we put it through some kind of die. On the other side of the die, it has a smaller diameter. Now the die design is kind of important. There's usually what they call a reducing surface and a bearing area and an entrance and exit angle. So the die itself looks something like this, and this is an axisymmetric problem. So if I can kind of show this this way. So it comes in, and then in the end it takes the bearing diameter. Not a great sketch, but I think you understand what I mean. Now, since it's bimetallic, we're gonna do this with a strip of copper on the outside edge. If you've used any jumper cables, if you purchased any jumper cables lately, it's probably bimetallic wire. It may not be completely copper anymore. But this is what we call an axisymmetric problem. There is an axis of symmetry, and if we look at one half of this picture and revolve it around the symmetry axis, then we have our problem. So in a way that was similar to our plate with the hole problem, where we had planes of symmetry, now we have an entire axis of symmetry. We can use special elements in Abacus where we only have to model that one plane, and then through the numerical formulation of the elements, it is able to calculate the stresses in all three dimensions, in the hoop direction, the axial, and the radial direction. So we're gonna do that. I'm going to make this mesh in HyperMesh. I'll provide the input models to you. I'll make the die. The die is a little tricky. We'll take a look at some pictures about die design. We're going to use rigid axisymmetric elements for the die. We're going to use deformable steel and copper materials for the elements that compose the wire. Typical drawing speeds can be on the order of 10 to 15, even higher meters per second. So we're going to pull this through here. We're going to give this a velocity of 15 meters per second. We're also going to put a tension in this wire this way, and that represents the force that's being used, and I think I've decided on 150 megapascals for that. We're also going to push it a little bit on this end, something like 10 megapascals. And we'll go through all those details. Now, the steel and the copper we're going to initially have just as modeled as this portion up here. We're going to tie the steel and the copper together. Okay, so we're going to use a tie constraint in Abacus, so we'll learn how to do that. It's very useful for doing something like this, or for tying meshes where some of the nodes don't line up. There's a kinematic constraint that can be established so that you don't have penetration. We're going to look at contact. We're going to talk about some issues with contact, and then we're going to end up using our adaptive remeshing because some of the distortion of the copper gets a little bit large. Now, as a reference for this, Let me pull up a paper. And a colleague of mine and his students put this together. I helped with the analysis, but this is from a few years back, 2011, microstructural evolution of copper-clad steel bimetallic wire. And so they were interested in what happens to the texture of the steel and the copper as you do this fairly aggressive drawing. This jacketing process is pretty interesting. I got to see it, got to go to the manufacturing facility. So you take a steel wire of a certain diameter, and then this jacket goes around it, and it's like it's if you can imagine kind of a banana peel in reverse. It's kind of like what happens with the copper. It gets wrapped around that steel. Now it's not maybe 3 pieces like a banana peel, but basically 2 pieces. It comes together, it makes a solid bond as it gets worked, and then it's bonded, it's adhered to this steel. So as part of this, there's a lot of information here about the texture. I'll provide this paper for you. And let me zoom in a little bit. So there's different diameters, different copper thicknesses, and there's different rates. So here's the rate of, like I said, 10 up to 20 meters per second. And there's a couple different steels they use. We're going to use a lower carbon steel analysis. We're going to look at something called 1055 steel. I have some properties for that we'll use, and I'll supply to you through a material library. And if I can scroll down here a little bit more, there's some of the metallurgy part that's very interesting, but the part that I wanted to show you is the finite element mesh results. Let's see where we're at. Okay, this is basically what we're going to do. We're going to have this die, and we're going to pull this bimetallic wire through the die, and we're going to take a look at the stresses that are in it and develop. So this will be an ABAQUS Explicit analysis. It'll be a relatively large deformation. When we take a look at strains, we're going to be looking at logarithmic strains. We're going to be looking at true stresses. Now, since we are going to be doing axisymmetric elements, we need to learn a little bit about Axi Symmetry and the types of elements that are available in it. And whenever you come up with a new analysis, I always recommend that you look through the example problems, look through and read through the theory part of Abacus, and get a good feel for what is involved in this. The nice thing about the hyperlinks is that you can go from one section to another pretty quickly in Abacus. But here's a typical thing for a figure for an axisymmetric situation. We're just going to model this as a 4-dimensional element in the plane. We're going to use reduced integration. And let's see if I can find the specification for axisymmetric elements. Now we're not going to use the N elements, but we are going to use the CAX4R. Let's see if I can. Here it is. Here's the axisymmetric without twist. So you can model this in Abacus accounting for twist, even though it's an axisymmetric problem and the section doesn't stay in the plane. You can model it with twist. I mean, the analysis will have it stay in the plane, but the results can be given with twist. It's kind of weird. So you can model torsion as an axisymmetric problem. But the type of analysis we're going to do is without twist. So we're going to use this basic CAX4R. So the C stands for continuum, AX is for axisymmetric, 4 nodes, and reduced integration. Now as you look in this element library, you see the S by some of these element designations. That means that that element type is only available in Abacus Standard. So in Abacus Explicit, we're kind of restricted. We have the 3-noded and the 4-noded. We have a 6-noded with hourglass control, modified element, and that is about it for ABAQUS Explicit. We're also going to need to use a rigid Axisymmetric element. And if we go down here on the left, I'm going to click on inertial, rigid, and capacitance elements. You see I have a couple hits for Axisymmetric down here. Goes into discussion of it. And for one-dimensional elements, we do have to be a little bit careful about our direction for our normal in our element ordering. Also with axisymmetric elements, the unit normals have to be all pointing in the z direction. And we'll come up with those issues. There's lots of errors that can pop up, but they're fixable. So we'll get through that. So we'll get to the definition of the rigid element. So let me bring up HyperMesh. I have it already kind of produced in here. And I'll give you the HyperMesh file, and I will give you the files that you need to import into Abacus. I'm a big fan of using HyperMesh and then importing. If you're really good and comfortable with the Abacus CAE interface, you can do all of this directly in Abacus CAE, as we've seen already. So here's my undeformed bimetallic wire, and here are my rigid elements. Well, they're not rigid elements yet, they're just two-dimensional elements, but we're going to replace this by editing the file that's created. So here's the copper strip, here's the steel, and this is my symmetry line. Basically what we're going to do in this analysis is we're going to have this die, we're going to push this die into the material, while at the same time this material is running forward at 15 meters per second, has some tensile force in it, and then it's going to move through this die, and we're going to get a reduced diameter for this wire. We're going to take a look at the stresses in the copper and in the steel. We're going to use the same copper properties that we did for the Taylor impact test, and like I said, I'll have some properties for steel we'll take a look at, but I'll provide you with a updated material library for this homework. You just import that in. Now, I just did a ruled mesh. They're fairly fine elements, so let's do a couple distance measurements. We'll get an idea of the size of these elements that we're dealing with. If I go into geometry, and there should be distance right here. Let me turn on my highlighter. Let me go back so you can see that. So I'm in geometry, and I'm going to go to distance, and then I'm going to do a two-node distance calculation. So here to here, we have a radial value of 0.821. I'm in the Newton millimeter second system. A total radius of 1.026, and then the thickness of the copper wire is was at 0.2052 millimeters. If we go back to this paper, again, we're basically looking at this low carbon steel type of analysis. Okay. All right. Now let's talk a little bit about die design. Here's my bearing area right here. It's usually fairly straight. Let's get a measurement on that. See what I'm using for that. I'm using about 0.7 millimeters. Let me call up a web page. I'll show you kind of the basics of the die design. I'll have to find it here. Alright, so I just did a Google search, and this is pretty typical of this die nomenclature. There's this flat spot right here. I know this is kind of small for a picture. There's a flat spot right here. That's the bearing length. So in ours, we're using about 0.7 millimeters. We have this R, this reduction angle. It's usually a fairly small angle, maybe around 18 degrees for a fine wire. It has this bell angle that's here, and So we're moving it through here. It's usually not this diameter D, right, little d right here. It's usually a little smaller than that, but it comes in through this bell angle and it gets reduced down, and then it comes out the exit down here. So to approximate this sort of shape, what I've done then is to have this shape right here. Okay, so now I'm not terribly satisfied with this analysis that I've done. And in order to get this to work, what I've done is I've taken this die and I'm going to move it into the material, which is a little bit, maybe a little bit unrealistic. That isn't really what happens. You got to get the thing kind of tapered down to a point a little bit, and then you draw it through to get it started. And you have a spool over here that winds this wire up as it's been drawn through, and that spool supplies the tensile force onto the wire. But without having to model all of that, I'm just going to move this die into the wire to get it started. This will have some initial velocity and it'll have a tension on it, and so this will be fed through the die after it's to its size that it really is. So one of the things that I'm not terribly satisfied with it is that I'll end up losing velocity of this wire, and at some point the analysis will stop before all of my wire has been drawn through. We can talk about some ways to maybe make this more sophisticated and change this, but it seemed to give me the response that I thought would be an okay simulation for the model that I was doing. But if you have some other suggestions, that would be great too. Okay. Now, one thing about Abacus is that, like I mentioned, whenever you use axisymmetric elements, like these 2D elements in here, the normals have to be pointing in the z direction. So let me reorient this in space just a little bit. And let's take a look at our normals. So I'm going into Tools, Normals, Elements that are displayed, and let's zoom in on this a little bit. I'm going to hit Display Normals, and here's the size. You can change the size if those arrows are too big, and for some reason they usually are pretty huge. If I can bring this down a little bit, get a good angle on this, and we can see that those normals in this case are pointing in the proper direction. Okay, so those are the arrowheads on this side. Now initially when I made this mesh, the arrowheads were pointed in the wrong direction, just based on the way that I made this, and it gave me a negative area for those elements, and it caused an analysis issue. Now the other thing that we're going to have to fix, and we'll do this when we're in CAE, is that the normals, or the connectivity of these two-dimensional elements, need to be in a proper direction in order for us to properly define the surface of this die. Now to construct this die shape, I made the flat, and I made an arc, and then I did a mirror on it. So some of these will have to be adjusted in order to apply our surface constraint in the model. So here's the hypermesh file. I'll supply that to you, and I'm going to export this as 3 different pieces: steel, copper, and die, and then I need to do a little editing on those in order to make sure that they're axisymmetric elements. Abacus is a little funny. Abacus CAE is a little bit funny. I will tell you it's easier to edit the input file by hand and get the element type in some cases than it is to change the element type in Abacus CAE. The axisymmetric library doesn't seem to show up unless you do things in a certain order. Maybe if you started with Abacus CAE and their part sketcher and everything, then it would be okay. but it's just kind of hard to do unless you start directly in Abacus. If you want to start in Abacus, I would encourage you to do that, and you can share with me how that works out. All right. So what I'm going to do next is I'm going to turn off a couple of these parts, and I'm going to export these as a solver deck for Abacus, just what is displayed, and I'm going to export this as the name steel. I'm going to put it in this folder to keep everything straight. Now it didn't really export, even though I hit save. It won't export until you come down here and hit the export button. All right. I'm going to go back to my model. I turn off the steel. I'll turn on the copper. I'll go to the export tab, and I'm going to go in here and type in copper, and then export it. And then finally, there's my die. And I'm going to export just what is displayed for the die. Right. Okay, so there are my files. Okay, I'm going to go in here into die. And I need to change that element type. That element type is a rigid Axisymmetric 2-node element. Okay, this is from a file I had generated previously. So I'm going to go in here, instead of T2D2, which is a truss element, and change this to rigid Axisymmetric 2-noded. These node sets, we can get rid of those. I don't think it'll hurt if they're in there, but we can get rid of those. They're empty node sets that I had created in my hypermesh file. Okay, and then saved it. Now I'm going to open up the copper. I'm going to scroll down here, and here's my node definitions. Notice that the Z is equal to 0. You need that for axisymmetric elements. I'm going to change that to CAX4R. Probably some node sets in here that I can get rid of too. I guess not. Okay. Oh, there they are. Alright, so we'll get rid of these. Now I did define an element set. I don't think it's necessary, but we'll talk about element sets when we import these into Abacus. So we'll save that file, and then the last one I want to import is my steel. Tell you what, let's do a search. And we're going to change this also to a CAX4R. Get rid of that node set if you want. Okay, so we have all those saved. Now I have Abacus started up. We have a model. I'm going to change the name of this model to composite wire. And I'm going to import the model. I need to find my working directory. And I want to import the input file. So let's import die. The copper. And the steel. as 3 separate models. Okay, and in the composite wire, we're going to instance these, but we need to do a little bit more work first. So let's get into the copper, and we're going to create a material property. We'll bring that in through the material library, and then we'll create a section and assign it. Okay, so to bring in your material library, we'll get into the material. We'll go to material library. Let's see, I probably need to reload this because I just made some changes. So let me do that. Alright, so let's try this again. We're going to go into copper, we'll go into materials. And if you double click on it and to like create a new material, then this material library tab will pop up. You won't see that until then. I'm going to go to material library, and we're in homework 8. So I'm just going to select this, and I'm going to add this to the analysis. Go back to my model. I'll do the same thing for the die and the steel. Now, as we mentioned before, it's kind of funny, I think, but even though it's the die is going to be a rigid element, it still requires that we put some material properties in there. We'll review those in a moment. So I'm just going to use steel for the die, and then of course for the 1055 steel, for the core of the wire, we're going to go in here and then add that same steel to that one. Let me make sure I'm in the current model here. Okay, there we go. Alright, so now I have the 1055 steel. Let's review these material properties. We have the density of steel, we have the elastic modulus and Poisson's ratio, and some plastic values. And I just picked a few points off of the stress strain curve, knowing the hardening values. There's a yield stress around 355 megapascals. And then in our copper, we're going to use here's our density. We're in the Newton millimeter second system. There's our modulus of elasticity, and here's a couple points on the plastic stress strain curve. Again, it's not very detailed. And if you were doing wire drawing analysis to get good results, you probably want to account for any kind of softening, change in modulus of elasticity due to heat buildup in the die. So these things really move pretty quickly. There's quite a lot of plastic deformation. Sometimes those thermal softening properties are kind of hard to come by. But for our demonstration purposes, for the analysis, this is okay. Let me just check the die, because I see I have steel in here in the copper section. Let's go ahead and just delete that. And I suspect I wasn't in the current thing here. Yeah, I didn't get that in there. So I'm going to go to my material library. See, you can tell what model is the current model by this underline right here. So I'm going to try to copy that into there. And looks like we have everything we need now for that. Okay. Now, Abacus, I find sometimes working with CAE is a little bit funny as to where you specify your rigid body definition in your rigid part. So I think we're going to do that in the assembly. Now, for some reason, I thought we did that in the individual part the last time when we did our Taylor impact specimen up against a rigid wall. But if we make a mistake, we'll fix it. Like I said in the previous presentation, that sometimes making mistakes is a good way to see things, because then you can figure out how to fix them. If everything is perfect, and then when I do these presentations and then something goes wrong when you try it, you may not know what to do. So let's take a look at this main model that we're going to use. We're going to create an assembly from these other parts. So I'm going to go in here and I'm going to right click on instances. I'm going to instance from a model, And you have to select these one at a time. Everything is lined up where it needs to be, so we're not going to offset these. And you want to hit apply and cancel, or hit OK. You don't want to do apply and then OK, because it'll instance it twice and make kind of a mess. So I'm just going to hit OK. I'm going to create another part from a model from the die, and I'm going to create another part from the steel. Just going to zoom in here and see what we've got. Now right now the steel and the copper are not connected. We're going to have to use a tie constraint to connect those. And we also need to do something with this. We need to turn this into a rigid section, and then we need to define the surface contact between the die and the copper. All right. Let's deal with the rigid part first. So let's see. Again, this may be the wrong place to do this. We'll find out here pretty soon. But we're going to go into constraints. I guess it would be in our interaction. We're going to create a constraint, and the type is going to be a rigid body using elements. We can select the elements by hitting this arrow. See if I can get this in the right spot to select everything. I'm a little bit short, so what I'm going to do is I'm holding down my shift button and I'm selecting these elements. Okay. Now I have all those elements selected. I'm going to hit done. Now I have a new surface. You see the B with the underscore, that means that's an internal set that Abacus uses. It's going to create that. We need a rigid body reference point. We talked about this in the previous analysis. We're going to create one. Well, I guess we need to create one from this. Let's do that. I'm going to hit this rigid body reference point, and it doesn't really matter where. I'm going to select maybe this bottom node if I can. Or how about that top one? Alright. Okay, now that I have that, now I can select my rigid body reference point. Kind of turns orange and then red when you select it. And I think that's all we need on this panel. I'm going to hit OK. So now we have this as a rigid body. Again, all the constraints only work by specifying constraints on the rigid body reference point. Alright. Now there's another very handy tool called the Display Manager. Okay, so if you go to Tools in Manager, or if you click on this Display Group Manager menu, this will bring this up. And right now, everything in the model is displayed. And you think you could edit that, but you can't. You have to create a new display group if you want to change what is displayed. So we're going to hit Create. And you can name this display group if you would like, but you don't have to. I'm going to go down here to Sets, and here we have the sets. So if you noticed, I had a set defined through HyperMesh as copper L's 2 and steel L's. It's the same elements that are composed in steel and copper for part 1. The -1 was appended by Abacus. So this is the model copper with the part copper -1 that is in that model. And if I want to get rid of that, then I can come down here and I can highlight that up here and then hit remove, and that should remove that part. I can remove other parts, but I'm just going to drag this to my other monitor and we'll get back to this in a moment. So the next thing I want to do is I want to make a constraint using a tie on a node region from the mesh by angle, and if I, by feature edge, let's try that. trying to highlight just the left edge, the right edge of that steel. It's being a little particular about this. So let me see what I can do to get that. It worked okay for me last time. Alright, so it seems to like it a little bit better if I look at the copper and not the steel first. So what I've done is, let me go ahead and add the steel back on. What I've done is I've removed the steel and I've got the copper right here. I'm going to do the tie constraint on a node region, looking at the mesh, the master nodes by feature edge, and then I get in here and those are now highlighted. So those are the master nodes. I'll hit done. Now I need the slave nodes. Can't edit the all group, so I'm going to create a new display group. I'm going to remove the copper and I'm going to add back in the steel. I'm going to do a node region on the mesh, and now if I can, there it goes, I'm going to highlight that edge. Okay, so now I've tied those together. Now here's the master and slave. We're going to use the defaults here. Okay. So now I can go back to my display group and I can add back in the copper. One of the great things about Abacus CAE that I really like is its ability to work with surfaces and sets pretty easily. I find that very convenient. Alright, so let's resize this a little bit. We need to make a contact surface between our rigid die and our copper. Now there's different ways to make surfaces, and let's try to define this as one of our surfaces. So in our assembly, we're going to create the surface. The name surface 1, you can change it if you want. It's going to be based on the mesh. Select the regions for the surface, and so I want to select these nodes. Now if you didn't get them all in one pass, you can hit shift and that'll highlight and add to your elements that make up that surface. And I'm going to select done for that. Now here's an issue. You see these yellow arrows, and you see here the yellows are on the wrong side. I need to get all of these on the same side. Okay, so I'm going to flip a surface. So I'm going to select the surface to flip. You might be able to do multiple selections, but I don't have very many, so I'm not going to worry about it. I'm just going to hit flip surface, and then I'm going to select those elements whose surfaces I need to have changed. And that was, like I said, an artifact of how I created my mesh in HyperMesh. Okay. Now that all of those are fine, I need to define the surface. Which side do you want? You want the yellow surface or the magenta surface? And we want the yellow surface to be our contact surface. We're going to create another surface. Select the regions. And now this one I don't see a feature edge capability. If you already have a set that's defined, you can select a set, typically. But what I'm going to do, and I will probably pause the video here while I do all of this, is I'm going to select the elements on the right edge. See, if I can rotate this a little bit better. You can specify views if you want. So let's see if I can do this. View, specify. You can do incremental about model axes, or you can do total rotation from 0, 0, 1. Let's try that. And that should line us back up, I believe, with our X and Y axes. Still looks a little slanted. Maybe that's my imagination. Okay, so to select this surface, I lost my dialog for that. Oh, there it is. To select this surface, what I'm going to do is I'm going to probably ought to turn off the die. Let's go back to our display manager. We'll remove the die. And I'm going to select all those. And I'm going to hit Shift, and I'm going to select some more elements to create that surface. You want to be a little bit careful. You see, notice down here at the bottom, it's got an edge selected here. We're going to get rid of that. And we're going to continue on up here. I'm going to pause the video. There's no need to you see me doing all of this, but we'll be right back. Alright, so I went through and hit Shift. Now if you have some extra elements that are been selected, you go down here and hit Control. Oops, I need to X out of my zoom. Go down here and hit Control. That will deselect those, and you see that go away. Alright, so now that I have that surface defined, I'm going to hit Done. And I'm going to add my die back in here. Alright, so there's my total shape. And again, I'm going to kind of zoom back in here. Alright, now we have the surfaces created. We need to set up a surface interaction. So that would be here, create interaction. And let's do surface to surface contact. We'll try that. If that doesn't work, we'll do something different. This will be set up in our initial step. The regions for the first surface. Okay, let's go surface 1 and highlight that. Okay, so that's the die. The second surface is that one. And if you change the names, it would be easier to find, but you can select highlight in the viewport and it'll show that surface. That'll be, we can continue on with that. It brings up this dialog box. Kinematic contact, yeah, I think that's okay. We're going to use finite sliding. We needed to make a contact interaction property, so we're going to create the property. Interaction property 1, contact. Mechanical tangential behavior. Now this is frictionless. Now there is a little bit of friction. We could probably model this as a frictionless behavior. But let's do penalty with coefficient of friction. In that paper I used 0.01. They usually have some kind of lubricant on this, and it's fairly smooth. Okay, under normal behavior, we're going to do hard contact, and we're going to allow separation after contact. So we'll hit the defaults on this. This is automatically selected now for this property, and you can add contact controls if you want, but we're going to hit OK. Alright. Now we're ready for our steps. We need some boundary conditions. boundary conditions for an axisymmetric problem have to be applied even on your axis of symmetry. Abacus does not automatically apply boundary conditions on a symmetry axis. There are good reasons for them not to do that. So we can either create a set and then apply the boundary conditions to the set, or we can just apply the boundary conditions right away. Let's try to create a set. I won't promise you this will work out great, but let's create a set by going into the manager, and we're going to create a new set that's going to be based on nodes, and we're going to call this symmetry nodes. We're going to select these. Let's try by feature edge, and if I can get this to work out alright, it will highlight all those nodes on this edge. Let's zoom in a little bit and see. Okay, so that worked out pretty good. So I'm going to select done and dismiss that. Now for my boundary conditions, I'm going to create the initial boundary conditions on displacement and rotation. We're going to select the symmetry node set, and we're going to apply. Let's think about this. We do not want any movement. We don't want any rotations. And on the symmetry line, we do not want any movement in the x-axis direction. So we're going to restrict that. Now we do want it to move in the y direction, the u2 direction. We're going to create a step. It's going to be a dynamic explicit step. We need a time for this step. Now in this first step is the one where the elements of the die move into the part. Let me see what I used on the analysis that I got working. When you do ABAQUS Explicit, these times are very very important to get right. Since it's kind of calculating it based on the wave equation in time, if you use a huge time, it's going to take forever for the job to calculate. So I used 0.0001 seconds. Right. We'll talk about mass scaling in a moment, but we'll hit OK. Let me bring my window back up. We want to have a predefined field on velocity, and here are eligible sets, but we're going to select from the viewport on the mesh. Change it back to 20. Let's go by angle. I'm going to select all those nodes of my wire. Now, if you look, I think it only highlighted the steel. So I'm also going to want to do the copper. So I'm going to press down my shift button and then click on that once it's highlighted. And now I have everything. Uniform translation on velocity, and it's in the 2 direction. And the way my die is down here, I want it to go in the minus y direction. And we said 15 meters per second, which is not an unusual number for drawing a wire. So I need to multiply that by 1,000 to get millimeters per second. So those arrows look like they're going in the right direction. And if you notice, that predefined field is in my initial step. That's where I wanted it. I want a couple loads. I'm going to create a pressure load on a surface. I'm going to create a surface. I'm going to select these elements down here, and notice you got a little extra, so again I'm going to go Control and click on these. Uniform with a magnitude 150 megapascals, and I want it to be in tension, so I'm going to put minus 150. Instantaneous application. And down on the back end, I want to push it through just a little bit. So I'm create another load. And I put 10 megapascals. And that'll push it through just a little bit. Okay. Alright, now I need one more. I need to do another thing in step 1. And that is I need to move my die into my material. So we're going to do that through a boundary condition application. It can be on displacement, on geometry, which can be my rigid body reference point. And we want to move it in the x direction. And we're going to move it in the negative x direction 0.192 millimeters. Now the amplitude that we're going to do, it's not a good idea to do displacement is an instantaneous application when you're in ABAQUS Explicit. When you're in ABAQUS Explicit and you're moving things around with displacements, and sometimes you need to do that, you should use an amplitude. One that's one that's recommended is the smooth step. So the smooth step starts out very slow. If you think of the time, it starts out very slow, it gets quicker, and then it slows down when it gets to the end of where it needs to go. So we're going to do a smooth step. And we'll have our first time at 0, and our amplitude would be 0 at that time. And at the end, time 0.0001 is what we put in for our step time, and we want to have a value of 1. Now again, the way this works is it's going to take this amplitude of 1 and multiply it by this magnitude of minus 0.192, and that'll be our total displacement. So you can make your time histories based on unit values and put the magnitude here, or vice versa. Now, unlike some of the other panels, this didn't automatically put in the amplitude card, so we have to go in here and select that amplitude that we just created. Alright, so I have my loads, my boundary conditions. I need one more step, and that's just basically to let the analysis run as it continues. So I'm going to create a new step, be dynamic explicit. See, now our options are limited. You can't do everything you want after a dynamic explicit step, but you can do these. And we need to figure out the time that we're going to use. Again, let me look at my previous analysis. And you will find that this is probably going to be a little taxing on your computer system. We'll go 0.005 seconds. You can reduce this down in time if your computer is having trouble. And in fact, you can probably cut this model in half and it won't be a problem if your computer is running out of memory or some other issue like that. It's not a terribly huge model. Alright, so then we'll hit OK for this. And I think that's everything that we need to do in this analysis. We're going to take our default outputs and everything. Before we get too much farther, let me save this file. And I think we're ready to create and run a job and take a look at the results. Again, if I've missed something, we'll find out pretty soon. I call this wire 535. The model is going to come from composite wire, and I'm going to hit continue. Okay, parallelization. Okay, let's try this. Let's try to use multiple processors, and hopefully I won't be disturbing any of you guys working on your homework today. But I have, I think I got 32 processors in this computer. I'm just going to hit 10. I'll show you. So there's how you do parallelization. Now, if you use multiple processors, it's going to check out multiple analysis tokens. When you check out multiple analysis tokens, that keeps someone else from being able to run Abacus. So be very cautious about that. Be very conscientious about it. So we're going to do that. The one thing we didn't do is we didn't set an adaptive mesh in here yet. But let's run this and we'll see the issue, and then we'll set adaptive meshing up. So now we're going to right click and I'm going to hit submit. And this takes long enough. It might take on my computer 20-30 minutes even. So I'm going to pause the video here, and then we'll pick up when this either has an error, which it just did, or when it's successful. So let's see what that error was. Let's go to monitor. And it says error checking out an Abacus license. Sometimes that happens. I might have lost VPN connection, or it might be because the teaching edition won't let you do parallel. Let me try to resubmit. And let's see what happens. If it doesn't, I'll reconnect to the VPN and we'll try it again. Okay, so it aborted again. Let me reconnect to the VPN, although it should have told me. So let's see. Maybe the teaching doesn't support parallel. Let's just get rid of that and let's try this again. Okay, so that must be it. So the teaching edition doesn't support parallel. Oh, well, maybe I spoke too soon. I have a different error maybe now. Oh, I have missing property definitions. Okay, so what happened is we did all that work, but I didn't create a section card for my elements. So let's go back in here into each part. Let's go into the copper. We'll get into there, and I need to go to property. So yeah, this is a step I forgot. We need to create a solid section using the property of copper, and then we're going to assign the section to all the copper stuff. And we're done. We're going to go into the steel. And make sure you're working with that part. We're going to go into properties, create a section, assign the section, and then we're going to go into the die. We're going to create a section. Now in this one, Let's see what our choices are. Solid, shell, beam, or other. Let's go beam truss. We're going to use the steel. And then we're going to assign section. Rigid parts cannot be assigned sections. Inertial can be assigned to rigid parts by selecting the menu item. Special inertial create. Alright, so maybe we don't need to assign that section after all. Some of these details I forget, but let's see what happens. We need to go back into our main model and we need to regenerate our instances. Let's see what happens now. Alright, so we have some errors. Rigid bodies with the reference nodes contained have no rotary inertia associated with them, and the rotational degree of freedom is not restrained. Okay, so let's go back. It's got an issue with my boundary conditions, it sounds like. Let's go in here. And it looks like that's the symmetry nodes. Okay, so I need to take a look at my boundary conditions for my rigid body. Okay, so I'm going to go back into my step where I created the rigid body, and so what happened is I need to set these two equal to 0. I can't leave them grayed out. Alright, so that's how you interpret that error message. Let's try it one more time. And I do practice these ahead of time before I make our videos, but sometimes there's a lot of things going on, and it's not always easy to remember every single thing. So the packager completed successfully. It says that it's running, and so I'm going to take its word for it, and I think finally this time I'll get to pause the video, but we'll take a look at the results when they stop. Alright, so it's been a few minutes, but the job is still running. But it's run long enough that we can get some idea of what's going on, and while it's running, we'll get set up for the next job. So I'm going to right click and click on results. It'll show the results so far. Now if you notice, this is very dark looking. It's because we have so many elements, so those element lines are kind of interfering with everything. Let's zoom in. Okay, I clicked on the stress contour, and let's animate it. Let's see what's happening. Okay, maybe we'll slow this down just a little bit. So my whole wire is moving forward at my 15 meters per second. This die is being pushed in. That's during step 1. And then step 2, it just runs, and it keeps running through there. Now let's pause this and step it through a little bit. We start to see some element distortion. Now our tag constraint is working pretty well. All of these copper nodes are still connected to the steel nodes, but look at some of these elements. They're very diamond-ish shaped, and they're getting more and more distorted, and that looks pretty ugly there. It's even pulling away. So what we're going to do is we're going to go back and add some adaptive meshing. So we're going to let this one continue to run, and while that's doing that, let's get back to our model. And we're going to put a little adaptive meshing. We're going to go into, let's see, where are we at? Should be an other feature up here. Let me find it. Okay, we need to select the step module, but up here it says Other. We're going to set an adaptive meshing domain. So we're going to go into the manager. I started in step 1. And we're going to use adaptive meshing. We're going to select a region by sets. So we'll select copper. Adaptive mesh controls. Let's add some adaptive mesh controls. And we can change this, but I think the defaults are going to be okay here. If it doesn't work, we'll change it. We'll use the default frequency of 10 and hit OK. We're going to do the same thing in step 2. Alright, so we learned a little bit in class about our adaptive meshing. Let me save my file one more time. Sometimes these things crash. And at this point, I'm just going to kill this off. Let's load the results one more time, but I think it's getting wildly distorted. And it's taken forever to run. Okay. So if it keeps going like that, it won't last very long. It's going to have some problems. Before we kill it, let's monitor it. Let's take a look at the energy. The energy looks fairly stable. Okay, so that's a good sign. You see the kinetic energy is kind of bouncing around a little bit. Something to kind of watch out for. Alright, so we're going to kill this job. And then I'm just going to resubmit. Alright, and once again I'm going to pause the video and we'll get back to it when we have something to look at. Alright, well, it's been about an hour, and let's take a look at the results. It's still running. Okay, it seems to be going okay. Let's zoom in on the bottom of this. You can see the adaptive meshing is doing pretty good. It's keeping those from getting terribly distorted. Let's turn off the lines. I think it might look a little bit nicer. We're going to go to Options, Common, and we're going to apply Exterior Edges, Feature Edges. There we go. And so now we can see the interface between the copper and steel. This is the von Mises stress. We get a little pile up of material here. I don't know if that's terribly realistic. We can change this to other stress components. There's the 2-2 stress. So that would be in the Y direction. 1-1 stress would be kind of in the radial direction. And then the shearing stress down here, S12. Alright, so one of the things about this analysis that makes this a little bit tricky is I'm not completely sure I've modeled the physical process completely accurately. It may be that I would want to do a displacement on these nodes. I remember at the time I did this analysis, I wasn't completely happy with it, but these can be a little bit tricky. I've noticed that if you are very good at modeling the physical process within reasonable physical parameters, material properties, displacements, amount of plastic strain that you would see in a real situation, that Abacus does a pretty good job. If you start to deviate from physical parameters appreciably, then your analysis will tend to break down. So what I would suggest for you to do is see how this analysis runs for you. See if you can find any way to model drawing of a wire a little more accurately. One last thing I want to do before we finish up is we can compute a percent reduction in area. Let's turn these nodes back on. I also want to show you how to sweep this to make a three-dimensional image. Before we do that, let's just stop this at the last frame, and we'll put the exterior edges on so we can see those. And in this area, let's come up with a new radius for this bar. So we're going to go Options, Tools, Query, Node, and we want to find the coordinates. Now, I may not have turned the coordinates on. Okay, here it is, Deformed Coordinates. So in the X direction, we got 1.0262. Let's compute a percent reduction in area. Oh, those are the original coordinates, sorry. The deformed coordinate is 0.9257. So if we want to compute a percent reduction in area, we can go through it here. So reducing the formulas down. Let me grab my calculator. And so we have about a 19%, we got an 18.6% reduction in area. That's pretty good. That may be a little bit more than what we would do in a single pass in a wire drawing die. Okay, so that may be some of the issue. So if you wanted to, you could change that analysis so that we didn't have quite as much reduction in area, and see if that helps out any. Alright, so one last thing I want to show you. So if we go into View, ODB Display Options, Sweep. Now we can sweep 180 degrees. I'm going to change that to 18 segments. And let's go back to our feature edges only, and we can find this in 3 dimensions, and we can animate it as well. Okay, so there's our die pinching in, and again, this is our shearing stress distribution. Alright, we'll give that one a shot. Let me know how that works out, and if you have any suggestions.